Welcome back to the sixth details video about the MEMSIC high performance 3-axis magnetic sensor. In the previous video we covered interrupts, its continuous measurement mode and the obscure option to disable measurement on certain axes. Card here, link in the description. In this video I want to cover the rest of the configuration options so we can move on to more interesting things. Enjoy! We've already covered all bits in the status and internal control registers, but for these 1, 2, 3, 4, 5, 6 bits. And we won't cover the enable SPI 3-wire mode bit here because we are using I2C. So these last 5 bits are all working together somehow, and they have something to do with the magnetization of our sensors. Short recap from part 3, card here, link in the description. Our little chip uses for each of its 3 channels XYZ a Wheatstone bridge consisting of 4 magnetized AMR sensors. And there is a little coil there under the sensors somewhere, this is just the principle here, which you can use either to set the magnetization of our 4 AMR sensors in the default direction, that would be a set, or is called a set in the datasheet, or you can reverse the magnetization of our 4 AMR sensors, and that's called in the datasheet a reset. Resetting or inverting the magnetization of our 4 AMR sensors also inverts the output of our Wheatstone bridge here. In that third part, we also implemented the reset and set command simply by writing a 1 to these bits here in the internal control register 0. Now, here's the first of our up to now uncovered bits, the auto SREN or enable automatic set reset feature bit. And that's the full documentation in the datasheet for that bit. So yeah, writing 1 will enable the feature of automatic set/reset. And yeah, this feature of automatic set reset is nowhere else mentioned in the datasheet. Yeah. The next mention of that bit is in the documentation of the enable periodic set bit here in internal control register 2, which enables a periodic set operation, and it requires the auto SREN bit, this one here, to be set to 1 to work, and also the enable continuous measurement mode bit here set to 1. But yeah, that's enable periodic set and not enable automatic set reset feature. So we will have to experiment here. How often that periodic set is carried out can be determined by the next 3 bits, which range from 000, meaning 1, that is on every measurement a set is carried out, to 111, meaning only every 2000 measurements a set is carried out. So it seems, the datasheet doesn't explicitly state that, but it seems if you are in continuous measurement mode, you can every nth measurement carry out a periodic set if the auto SR enable feature is activated or something like that. Let's have a quick look at the implementation. Of course, I define another enum auto set reset with a byte all 0 as the default. That's the auto set reset feature disabled, and the right bit here for the internal control register set to 0 for auto set reset enabled. The one enable bit plus the three, well, let's call them counter bits in the control register 2, I put into one enum because, yeah, we are handling them together all the time, so it really doesn't make sense to split them up. Anyway, yeah, a periodic set disabled, of course, all 0, and then we have here all possible combinations, giving us a periodic set, yeah, every measurement up to, yeah, only every 2000 measurements. Then we have two public methods to get these bits into our shadow registers, and that's set auto, set reset, and set periodic set. And of course I define the related bits and bit masks here in the private part of my function. So here we have the control register 0, auto, set, reset, enable bit, and further down in control register 2 we have the periodic set bits. So these are the 4 most significant bits in control register 2. We've implemented such methods before, several times before, so I will just mention that set auto, set reset sets the according bit with some bit banging in the control register 0 shadow register, and set periodic set sets the according bits in the control 2 register shadow register. Now for the sketch, and we'll start out with a variant that really should work. So all the interrupt stuff from the last video is gone. We just do serial begin, set our wire speed, do MMC begin here, and then we set continuous measurement mode to 20 Hertz, so 20 measurements per second. And then I set here the periodic set to every 100 measurements. So we will have a periodic set approximately every 5 seconds. Yeah, my loop has a delay of 100 milliseconds in it. And then I enable the auto set reset feature here. And of course, at the end, I write my config. In the loop, we have again a little bit of a switcheroo thing going on here. So every time I go through the loop, I increment my counter count here. And if I reach 25, then I do a reset sensor magnetization. Remember, this should flip the outputs of our sensors. And then at 50, I reset my counter to 0. So about every 50 loops, we should have a reset of our sensor magnetization, the flip in our output. But at the same time, remember, every 50 loops, we do a periodic set. So yeah, the result should revert again to normal output. Anyway, we have a delay 100 here, the usual. Then I read my access output with some error handling. I don't print out any errors because I want to use the serial plotter again. And then I print out my 3 axes in milligauss. And here's the output on the serial plotter, and as you can see, especially here for the green z-axis, the sign of our output value flips around our 0 line more or less regularly. So that really works as expected. However, the datasheet leaves a lot of questions unanswered. Let's start with that conundrum. So to set enable periodic set reset, we also need to have auto set reset feature enabled, and we need to have the continuous measurement mode enabled. But the datasheet doesn't state explicitly anywhere that we also have to choose a continuous measurement mode frequency that is not off. So in theory, we can select a periodic reset set here, and we can enable continuous measurement mode, but choose here as the frequency off, so no continuous measurement. Let's try that one. Just a quick reminder, in part 4, card here, link in the description, when we implemented the continuous measurement mode, we had here two off options. We had continuous measurement off, which leaves the enable bit set, but sets the frequency bits all to 0, meaning, yeah, off. And we had continuous measurement disabled, so the default after reset, where all the bits are set to 0. So the first change in my sketch, and the only change for now, is that I set continuous measurement off. That's all. We should now see that the chip is taking absolutely no measurements. And indeed, if we look here at the serial monitor, yeah, we are flatlining. We are completely flatlining, as expected. Now, since we don't take any continuous measurements anymore, I added here two take magnetic field measurement commands here in the loop, each time waiting 10 milliseconds afterwards, and I reduced the main loop delay accordingly to just 80 milliseconds. So we should see approximately the same picture again, or maybe not. And yes, our chip seems to be a wee bit behaving funny. So, as you can see, obviously the measurements are not updated twice every 100 milliseconds. There's something very odd going on, and we also can't really... Oh, yeah. Here we have an inversion. So my reset command set in, but it is... Yeah, it does something, but it's not happy. So, yeah, we cannot use that combination of config bits. That's clear. So, as a first consequence, we can delete one of the options here for the continuous measurement. Obviously, it makes absolutely no sense to have continuous measurement enabled bit, but then select off as the frequency. Now I've completely disabled the continuous measurement in our setup and left the rest unchanged, which is definitely not supported, but we still have a look-see. And would you believe it? We do not have any inversions. Yeah, the z-axis green, if it's positive, we are in the standard magnetization. So I still do, yeah, every 50 loops a reset of the magnetic field, but that doesn't show up. So obviously the chip does now, with these settings, automatic set before each and every measurement. But our periodic set is still configured to only, do a set every 100 measurements. So let's just delete that option here, and continuous measurement disabled is 0 anyway, so remove that too and have another look at the serial plotter. And indeed, just that one config bit here, enable automatic set reset, which is really just an enable automatic set, obviously suppresses our every 25 loops reset of the magnetic field, not software reset. Oh, so the bit for alone, it does something useful. That's nice to know. They should have written that into the datasheet. Yeah. Anyway, to summarize the automatic set of the AMR sensor's magnetization. The magnetization is automatically restored to the default direction each time before we command a single magnetic field measurement. If we are in continuous measurement mode, we have to use the periodic set configuration option to achieve the same thing. And the periodic set of the AMR sensor's magnetization every nth measurement is restoring the default direction every nth measurement in continuous measurement mode. And for that to work, automatic set, has to be enabled, and the continuous measurement mode has to be enabled. Otherwise, it won't work. All other bit combinations in the internal control registers lead to, funny results. And what it is good for? Well, the pre-magnetization of our AMR sensors can be, degraded, corrupted, and so on by external magnetic fields. So, depending on the application, it might be a good idea to set it into the default direction each time or every nth time before you take a measurement of the magnetic field. We've now covered each and every bit in the status and internal control registers, but for the SPI 3-wire mode bit, which is really useless when we are addressing the chip via I2C. But I got a little bit time left, so let's talk a little bit in depth about the set and the reset operation. We covered those in part 3, already carded, link in the description, and we know what they are doing. I mean, the set operation, we talked about that in length, is setting the default direction of the magnetization in our RMA sensors, and the reset operation is inverting the pre-magnetization of our AMR sensors and thus inverting the output of our Wheatstone bridge configurations here. But what is it used for besides testing if the auto set enable and the enable periodic set stuff works? This is explained at the very end of the data sheet. Well, not the very end, there are 2 more pages after this covering soldering, temperature profiles and package outlines. Anyway, the set and reset functions can be used to remove an error associated with bridge offset changes. So, what's a bridge offset? If our left and right arm in our Wheatstone bridge configuration here are not completely symmetrical, then you get an asymmetric output out here, meaning that our 0 Gauss point will shift. So, how does that bridge offset look like in practice? I have here now in my sketch a minimal setup, so just the serial stuff, my wire stuff, and then a begin for my little chip. And in the loop, no switcheroo magic, just a delay of 90 milliseconds. Then we take a field measurement. We wait for 10 milliseconds until that's finished. I read the axis output and I'm now outputting only the x-axis here in milligauss. And if we look at the output of the serial plotter, we are here generating a value in that orientation, and I can change it a little bit. I'm searching for the maximum value we can achieve of about-ish, 129, let's say 130 milligauss. And if I turn that around now 180 degrees, we would expect minus to 130 milligauss. But what we actually get, if I do that here, we're here at the minimum, little over minus 300 milligauss. So things are not symmetric at all. So just assuming that our 0 Gauss point is at the middle of our value range, we implemented those raw axis output 18-bit signed and 16-bit signed, as well as the raw axis output 16-bit Gauss and raw axis output 18-bit Gauss, also in the third part, already carded, a link in the description. That's just an approximation, or an educated guess, but it's not the reality. Now, instead of turning our sensor 180 degrees around and guesstimating things, the datasheet suggests to use the set sensor magnetization and the reset sensor magnetization. Remember, reset also flips everything 180 degrees to determine the bridge offset. And so here in my sketch, I reactivated the switcheroo stuff. So at a 0 count, we do a set sensor magnetization, and at a 50 count, we do a reset sensor magnetization. At 100 counts, we start anew. And on the serial plotter, and I didn't bother with the second camera this time because I won't move the sensor, we can see how, our reading flips. But the top line here is 400 milligauss and the bottom line here is minus 400 milligauss. So things are not symmetric. And here comes the procedure prescribed by the datasheet to get rid of that. And there it says you should perform 5 steps. First, perform a set, then perform a measurement, and your output will be the measured magnetic field positive plus the offset. And then perform a reset, do another measurement, and this time the output will be the negative magnetic field plus the offset, and then do some math to either calculate the actual magnetic field or the offset. And that's exactly what I'm doing now in the loop. I have 3 32-bit signed integer variables here for my raw X value with a set magnetic field and the raw X value for the reset magnetic field, and the offset I will calculate. So I wait 82 milliseconds. I added the delays up to 100 milliseconds. And I do a set sensor magnetization, then I take a magnetic field measurement, then I read my axis output, and then I store my raw axis output that is unsigned, remember 18-bit, but I convert it into a signed integer in my raw X set. Then I reset the magnetization. Then I take again a magnetic field measurement, I read again out my axis output, and I store that result in raw X reset. And then the offset is simply calculated as the average, the middle line between the set value and the reset value. And I print all 3 out here. And that's how the whole thing looks on the plotter. And I think you can see here, the blue line is my set value, the red line is my reset value, and of course they are mirrored around the offset I'm calculating now, the green line. And I forgot to mention that I also output here, that's the absolutely straight fixed line. the 2 to the power of 17 middle value of my 18-bit raw values. So, yeah, and obviously there is a difference between the fixed offset we used up to now to get to our center value and the green now calculated offset from the set and reset values. I'm now printing out just the offset and my fixed 2 to the power of 17 values to show you a weakness of that method. So this is all good and fine, and we have here our, with a little noise, but that's naturally from our signals we use to calculate the offset, our offset line. And here's our fixed line. And if I turn very slowly, nothing happens with our offset. But if you have a fast movement, things get ugly. And there's a simple reason for that. We take two measurements, and there is a time delay, of course, between the measurements. So if our magnetic field changes in that time frame, or our sensor is moved within the time between our two measurements, our offset value is off. So this really just works as long as you perfectly, as long as you don't move the sensor or the external magnetic field doesn't change. Food for thought. That's it for today. Next time we will try to actually put these offset measurements to a good use, and we will also have a look on the actual temperature drift of that thing. I mean, that's the whole reason we measure the offset in the first place. Till then, bye.